Bohr's equations when we consider the nucleus to be flexible and not fixed. So when we don't consider the nucleus to be heavy, we know that the nucleus and the electron both will be revolving around their common center of mass. But the Bohr's equations which we have derived till now, they assume that the nucleus is at rest. But we know that in reality, the nucleus and electron both will be revolving around the common center of mass. So for that, we are going to modify our Bohr's equations a little bit. So what we'll do is the equivalent of this can be considered that the mass, that the nucleus is at rest and the electron will have a reduced mass. So instead of mass, we will consider it as a reduced mass mu, which will be mm upon m plus m. And after this assumptions, we can now use the Bohr's equations and it will yield us the correct answer. So how we made this assumption that is part of the mechanics, which we will not discuss here, but just know that this system is equivalent of this system. And for this system, we already have our Bohr's equations. So let's do that. So we know that the radius of nth orbit is proportional to n square by z upon me. So this was our original equation. But now for the reduced mass, we will write this as Rn is proportional to n square by z me mn upon me plus mn. Now, if you remember this 0.529, that was calculated by using the mass of the electron. Its value, which was 9.1 into 10 to the power minus 31, that was included in 0.529. So we'll do that again. So we'll take this n square z by me together and this part will take out me plus mn upon mn. So this part, except the part of me plus mn upon mn, the rest of the part is still the same like our original equation. So our modified equation will become Rn into 0.529, sorry, Rn is equal to 0.529 into me plus mn upon mn n square by z angstrom. So again, original equation was 0.529 n square by z. So we just, where me was there in the denominator, will add mn upon me plus mn there. So this is our modified radius of the nth orbit. Now similarly, the energy when we derived, that was proportional to z square by n square me. So again, in our case, me will be replaced by reduced mass, and this part z square by n square me, that will still be the same, which is minus 13.6 z square by n square. So we'll multiply that by mn upon me plus mn, and that will be our new equation. So we are going to use these two equations if we consider the nucleus to be flexible and not fixed. Now let's do 6.46, where we need to take into account the motion of the nucleus and how much in percentage will be the binding energy change, how much the Rydberg constant change. So let's find that. So binding energy is this. So like we discussed before, it will just multiply it by mn by me plus mn. So what we need to find is change in binding energy upon original binding energy into 100. So the original is the accurate one. So we'll write that and we'll do this and we'll get our answer, which is 0.054%. Now binding energy we can write as some constant into Rydberg constant, which implies delta Eb is equal to that constant times delta R. So delta Eb by Eb is equal to delta R by R. We have already calculated that. So delta R by R in percentage is also same as 0.054%. So these are our answers. All right.